Okay, so we are going to do question 8A, and we'll also do B because it's not too bad. So scrolling down. Okay. 8A. So 8A says graph f of x equals log base 2 of x and g of x equals 2 to the x on the same coordinate grid and clearly label which is which. Also label at least 3 important points on each graph. Okay, so let's start with the first function, which is just f of x equals log base 2 of x. So let me write that down. Okay, so there's a really nice theorem in the book. Let me just get a page that way in case you guys want to know what page it's on. So page 473 gives you some properties of logarithmic functions. So it tells you that if you have f of x equals log base a of x, there are 3 points that you know for sure are on your graph. So you know for sure that you have the point 1 over a and then -1. Then you also know for sure that you have 1, 0, and then a1. So that's really nice because then when you go to graph something like this, you just have to remember that like rule that we have, and then you've automatically got 3 points that are on your graph. So that's nice. So let's go ahead and apply that. In our case, our a would be 2 because that's our base here. So we know that we have the point 1 over 2, -1. And then we also have the point 1, 0. And then we also have the point 2, 1. So there is a similar theorem for exponentials. So we can use that as well. So on our exponential equation, which is g of x equals 2 to the x. I'm not too sure what page it's on. Let me see if I can give you guys a page number in case. Looks like it's on page 452. So on page 452, it tells you that if you have f of x equals a to the x, you definitely have the points -1, 1 over a, 0, 1, and then 1a. So you might look at these and notice, oh, these look just like the ones that I know that I have for a log, except my coordinates are flipped. So like for a log, we know we have a, comma 1. And then for an exponential, we know we have 1, comma a, which that's a good observation. And that just goes back to the fact that exponentials and logs are inverses of each other. So if my log has the point 1, 0, then my exponential has the point 0, 1. So if you can remember 3 points that for sure every log has on its graph, then by default you know 3 points that an exponential has because they're just the coordinates flipped. But let's go ahead and apply this to the exponential that we're given. So we for sure have the point -1, 1/2, 0, 1, and then 1, 2. Okay, so that's going to be helpful for when we do our graphs, especially because this problem specifically asks for you to label 3 important points on the graph. So that's cool because this theorem or these like properties just go ahead and give you 3 important points. So that's nice. Let's go ahead and do our log first. So I know that my log has the point 1/2, -1. Is about there. I know that it has the point 1, 0, which is here. And I know that it has the point 2, 1, which is here. So I'm going to go ahead and do just a rough sketch of this. Okay, and this is the graph of f of x. Okay, so now let's do g of x. So just graphing those 3 points that I have for g of x. I've got -1, 1/2. I've got 0, 1. And I've got 1, 2. Okay, so just giving you a rough sketch of this one. That is g of x. And that would be it for graphing them. So as long as you have an idea of what the general shape of an exponential is and what the general shape of a log is, and you've got those points and you know some like basic properties, like you know that f of x shouldn't cross the y-axis and you know that g of x shouldn't cross the x-axis, then you're good to graph these. So going on question B that says, are these two functions inverses? So if you remember, the property of inverses is that like the inverse of f of x is just that like function reflected across the line y equals x. So if we look at what that looks like, we can see that this is true for our two functions. So you can see that one is definitely just the other reflected across that line. But you don't even have to like really remember that to be able to say so. If you just remember that logs and exponentials are the inverses of each other, then you're good. So this is yes. Do either of you have any questions on that specific problem? Okay, sweet. Do either of you have another problem that you want to see me do? You can send it in the chat or whatever. And you weren't here, Madison, but I said to Noah, like, it's just you two, so you can stay as long as you want, or you can go whenever you have to. You don't feel like you need to stay just because it's the two of you. Like, if you're good to go. You don't have to stay, but I'd love to have you guys stay. So whatever's fine. Okay. Okay, so number 5. Let me go to number 5. Okay, sweet. So 5 says graph the following piecewise defined function. So we're given g of x is equal to 2x minus 4 when x is between -1 and 2, and then g of x is equal to -3 when x is between 2 and 6. So I tried to explain it to one of my classes this morning, that when you graph a piecewise function, it's like graphing a regular function. You just have to break it into pieces almost. Hence the name like piecewise function. So you can see with g of x, we have kind of two pieces of it. So we have that piece that's 2x minus 4, and then we also have a piece that's -3. So we'll just take it piece by piece. Also, if I say piece any more time. So our first one is 2x minus 4. So to graph this, I'm just going to make a little chart because I think that's easy. So if I want to graph 2x minus 4, I'm going to make a chart with some x values that I'm going to input, and then I'll keep track of their outputs. So I was telling my class today that you always want to plug in your endpoints on the intervals. So 2x minus 4 is defined where x is between -1 and 2. So even though 2x minus 4, even though that's not defined where x is actually equal to 2, it's just where x is up to 2. So you can see that like my interval is x is less than 2. It's not less than or equal to. You're still going to plug 2 in. That's just going to tell you that at that point you have a hole. So you actually have like an open circle, not a closed circle. But that'll make more sense once I actually graph it, I think. So I'm going to plug in my endpoints of my interval. So -1. I'm going to pick a point that's in between -1 and 2. So I'm just going to go with 0 because that's always a nice one. And then I'm also going to plug in 2 because that's my other endpoint on that interval. So plugging those in, when I do -1, that's going to give me -6. And that's just because 2 times -1 minus 4 is equal to -6. And then when I plug in 0, I get 2 times 0 minus 4 is equal to -4. And then when I plug in 2, I get 2 times 2 minus 4 is equal to 0. So now I've got some coordinates there. So I have -1, 6, 0, -4, and 2, 0. So I will go ahead and plot those. So I've got -1, 6, -1, -6. I knew that didn't sound right. Sorry, guys. Okay, -1, -6. Just down here. And then my next one was 0, -4. So then this is where it becomes important because my next term was 2, 0. That was my next coordinate paragraph. But remember I said on my interval up here, it's only defined where x is less than 2, not where x is equal to 2. So it's important that when we graph the point 2, 0, we do an open circle there. So at that one, I'll have an open circle. So then I'm going to try and make a nice line here. Okay, good enough. And so now that's my first piece of this function. So now to do my next one, it's -3, where x is greater than or equal to 2, and less than 6. So remember that graphing -3 just looks like the horizontal line at y equals -3. But I only need to graph it from where x is 2 to where x is 6. So to go ahead and do that, at 2, I know that it's -3. And that's important that that's a closed circle, that it's shaded in because this symbol is greater than or equal to. But it's important that when I graph at 6, that I make that an open circle because it's just less than, not less than or equal to. And connecting those, that's what your graph should look like. So there's really like a few steps or things that you have to look out for on these. So you have to graph each piece, just take it one by one. Make sure to plug in your endpoints, but make sure that you graph those points accordingly. So if you have like less than 2, make sure that you don't shade in that point because it's just less than, not less than or equal to. So there's just like a few components of doing a piecewise function. Okay, if you guys are both good on this one, you can feel free to send another question in the chat or whatever you guys want to do is fine. If no one else has any questions, I can totally stop here. But if you guys have, oh, cool, I got another one. C on number 11. Yes, I can. Sweet. Okay. So C. So I think number 11 is all log questions. Yes, it is. Okay, cool. So this is kind of where you just need to remember how we defined logs at the very beginning. So like if you have, let's say log base A of x equals y, this is the same as saying a to the y power equals x. So this is going to help you solve this problem. Whichever class you're in, I know that I definitely introduced that little like trick that I learned, that you just draw like a little like arrow going from the base over here to here. And that tells you that this is the same as x to the third power equals 1 over 8. Oh, wait. Yeah, I did that right. But that's the same as just using how a log is defined. So being given log base x of 1/8 equals 3 is the same as saying, okay, what power, or sorry, x to what power gives you 1/8? So then to go ahead and solve this, we can just, if you don't know right away by looking at it, we can just take like the cube root of both sides. So then we get that x is equal to the cube root of 1/8. And so that's just asking you, what number do we multiply to itself 3 times to get 1 over 8? So the answer to this one is 1/2. And that's because 1/2 times 1/2 times 1/2 is going to give you 1 over 8. So the answer for this one is just x is 1/2. Anyone have any questions on that one? Okay, awesome. So like I said, feel free to ask any other questions you guys have. I'll just give you a little bit to think if you have any questions, and I'll just sit here. But if you're done and you don't have any more, you can just let me know and you're totally good to go. $20. Yes, I can. I don't even know what question 20 is. Oh, here we go. All right. So another fun one, graphing logs. Okay. So it says to use transformations to graph the following function. So we're given f of x equals ln of x minus 2. So first of all, our like starting function would be ln of x. So the important thing is to realize that the transformation that's going on is that now we have ln of x minus 2. And then we just need to know what that does. So first of all, let's just remind ourselves what this does. So when I have ln of x minus 2, it means that I'm shifting the graph of ln of x 2 units to the right. So this just means that we shift horizontal 2 units to the right. Okay, so this is going to help us. But first of all, in order to even like really shift our graph 2 units to the right, let's identify 3 points that are on my starting graph. So let's identify 3 points on the graph of ln of x. Okay, so to do that, we're going to be using the same thing that I said before, where if we have a log, we automatically know 3 points that are on its graph. So to go ahead and write down what those points are specifically, we just need to remember that ln of x is the same as log base e of x. So using that, we know that the point 1 over e, -1, is on our graph. E, comma 1, and then 1, comma 0. Okay, so that is ln of x though. We're concerned about ln of x minus 2. So this is a horizontal shift 2 units to the right. So what that means is that I'm going to take these 3 points here and I'm going to add 2 to their x component. So I'm going to take their x component and just add 2 to it. And that's because I'm shifting everything 2 units to the right. So down here it says 3 important points on the final graph are what? So I'm going to go ahead and just like write the transformed points down there. So if I shift these 3 to the right by 2, that gives me 1 over e plus 2, comma -1, gives me e plus 2, comma 1, and then 3, 0. So in order to actually graph this, yes, yeah, good. So if your equation that you're given was like e to the x, then yes, the coordinates would be switched. So you would have like the opposite of what we have here. So instead of having like the point E1, we would have 1E. Question 5, yeah. Let me make sure. Question 5, I think, was the one. Let me double check though, before I just say yes. Not question 5. I think you're thinking of question 8. That's the one where we graphed log base 2 of x and then 2 to the x. I think that's the one you're thinking of. Yeah. Yeah, this is just like it, except in this question, we're just graphing ln. We don't have to graph like its inverse or anything. But yeah, good connection there, because this is using like the same techniques. Okay, so in order to actually graph these points though, you'd have to have an idea of what E is. So E is roughly 2.718. So in graphing things like 1 over E plus 2, in my head, when I do them on the graph, I just kind of pretend that E is 3. So I just approximate E to be 3, because that's pretty easy to graph and it's pretty close to what it actually is. So when our like first coordinate is 1 over E plus 2, comma -1, I'm just going to pretend that E is about 3. So that means now I have 1/3 plus 2, comma -1, which is just 2 and 1/3, -1. So that's a lot nicer to look at than saying, I'm going to graph 1 over E plus 2. So saying 2 and 1/3 is a lot nicer. So let's do that point. So 2 and then 1/3 and then -1 is like about here. How would we do that on the test since we don't actually? Yeah, you should just remember that E is about 3. So I mean, roughly E is like 2.718 something. But for graphing purposes, just try to remind yourself that E is about 3. So yeah, you don't technically need a calculator. Just, yeah, try and remember that E is roughly 3 for graphing purposes. Okay, so for our next point, it's E plus 2, comma 1. And if E is about 3, this is roughly about 5, 1. And then my last point is just 3, 0, and that one I don't need to do anything to it to change it. All right, so now I've got 3 points, and I'm just going to draw my graph. So the last part on number 20 asks you for the domain of f of x. So just remember that for log functions, their input always needs to be positive. So our input is x minus 2, and that just needs to be greater than 0. So I get that x just needs to be greater than 2. So my domain is 2 to infinity. And you can see based on my graph, that's definitely reflected because you can see the points that are plugged in are all greater than 2. So you can see like my graph starts at about 2 and just continues over, but no like negatives are there. So you can see that that is true based on the graph. Okay. Anything else in reference to this problem or any other problem in the study guide? Okay, you're good, Noah. Yeah, if you're good, Noah, you're okay. Good luck studying, Noah. Yeah, good luck on the final. Yes, we can definitely go over the simplifying aspect of number 9. Number 9, yeah, for sure. Number 9 is a little tricky. It's a bit of a rough one. Okay, so, so I think when, you know what, I'll just do the whole problem. It's okay. It's good practice. So I'll emphasize mostly on the simplifying aspect, but I'll just walk through the whole thing. So by solving the equation 2 to the x plus 1 equals 5 to the x minus 2, or 5 to the 1 minus 2x, sorry, misspoke. We want to take ln of both sides. And I know I've briefly explained this in recitation, that we can't make the bases the same here. So whenever you see a problem like this, your first thought should be, can I make the bases the same? Because then I can set the exponents equal, because that's usually the fastest way. But with this question, we definitely can't. So our solution is to take ln of both sides. So I get ln of x, sorry, not x, sorry, of 2 to the x plus 1 equals ln of 5 to the 1 minus 2x power. So the reason that we do this is because we have those properties of logs where we can take this exponent inside and we can move it out front. So this now becomes x plus 1 times ln of 2 equals 1 minus 2x times ln of 5. So remember that ln of 2 and ln of 5 are just numbers. So the thing I'm going to do with these on both sides is distribute these in. So it's just like there were a number there. So it's just like I had like a 2 out front and I distribute that in. Same concept. So this now becomes x times ln of 2 plus ln of 2 equals ln of 5 minus 2x times ln of 5. And the reason that I do this is so that I can group my x terms together, because I am trying to solve for x. So any of the terms that we see an x in, so like this one or this one, I'm going to group these together. So I get x times ln of 2, and then I move my 2x ln of 5 over. And that's equal to ln of 5 minus ln of 2. So since I am solving for x, I'm going to go ahead and pull this, or like factor, I guess you could say, this x out of both terms. So I get x times ln of 2 plus 2 times ln of 5 equals ln of 5 minus ln of 2. So my next step is to divide by ln of 2 plus 2 times ln of 5. And then this is just going to give me that x is equal to ln of 5 minus ln of 2 over ln of 2 plus 2 ln of 5. So like I mentioned in both classes, that this, like, it's not that this answer is wrong, it's just not in simplest form. So it's like before when you've given an answer like in a previous math class or something, and it's like, it's not wrong, but it's just not fully simplified. So that's what's going on here. So we're going to go ahead and take care of that simplifying. And this is just going to be using properties of logs. So we have that property that if we have two logs with the same base being subtracted, you can divide the things inside of them. So I'll write the properties off to the side, but we have that log base A of m minus log base A of n is equal to log base A of m over n. So that's what we'll use in the numerator here, because that's exactly what we have going on. So my numerator is equal to ln of 5 over 2. And now I just need to do my denominator. So we're going to use two little properties here. So one of them is that log base A of m plus log base A of n is equal to log base A of m times n. And another property is that r times log base A of m is equal to log base A of m to the r power. So this first one just says that if I have two logs with the same base being added, I can combine them by multiplying the things inside. And then my last property says that if I have an exponent if I have an exponent on what's inside of my log, I can bring it out front. So that also goes the other way though. If you have a number out front, you can bring it inside the log by making it an exponent. So first we'll use that on the denominator because we want to combine these two terms in the denominator, the ln of 2 and the 2 ln of 5. But in order to do that, we first need to deal with this 2 here that's out front. So I'm going to take this and I have ln of 2 plus ln of 5 squared. And I just use that last property to bring that 2 that's out front inside as an exponent. So now that I've done that, I can go ahead and combine these logs using the first property that I listed. So this is equal to ln of 2 times 5 squared, which is equal to ln of 2 times 25, which is equal to ln of 50. And that's my simplified denominator there. And so that's my answer to A. Yeah. I'll go ahead and do B. Well, would you like me to do B? Okay, cool. I'll do B then as well. So B is also using very similar properties that we just talked about, so this is a good one to do. So this is the same concept that I want to combine these two logs here. So I've got 1/2 log base 3 of x equals 2 times log base 3 of 2. So I definitely want to combine them. They have the same bases. So for starters, I'm going to move them onto the same side of the equation. So I have log base 3 of x, and so I'm going to move this other one over. So I get minus 2 log base 3 of 2 is equal to 0. So I just move them so they're on the same side, so it's easier to look at, and then combine them into 1. Just like we did on the denominator of part A, we have out front some numbers here that we need to deal with, and we need to move them inside as exponents. So this becomes log base 3 of x to the 1/2 minus log base 3 of 2 squared equals 0. Now that I've moved those inside, I can go ahead and write them as 1. So I get log base 3. And remember that when we're combining logs that are being subtracted, we divide what's inside. So this becomes x to the 1/2 over 2 squared, and 2 squared is just 4, equals 0. So I'm going to continue my work down here. So now we've got a single log. So remember, by the definition of what a log is, this is the same as saying 3 to the 0 power is equal to what's inside. So I have 3 to the 0 power is equal to x to the 1/2 over 4. This isn't too bad because we know 3 to the 0 is 1, because anything to the 0 power is 1. So I have 1 is equal to x to the 1/2 over 4. And to keep going with this, I'll multiply both sides by 4 just to get rid of that 4 in the denominator. And that leaves me with 4 is equal to x to the 1/2. In case anyone doesn't remember, x to the 1/2 is the same as the square root of x. So this is the same as doing 4 equals the square root of x. And then we know that that means x is equal to 16. Yeah. So the reason that this ends up being equal to 1 is that we have 3 to the 0 power, and anything raised to the 0 power is equal to 1. So like 2,000 raised to the 0 power is just 1. So anything at all raised to the 0 is 1. So over here, when we go from our, let me use a different color. When we go from our log form down here to the exponential form, so saying log base 3 of x to the 1/2 over 4 equals 0 is the same as saying 3 to the 0 power equals x to the 1/2 over 4. So I rewrite it like that form down below right here. And then 3 to the 0 power is just 1. So this just becomes a 1. Yeah, it's a good thing to remember because I feel like some of those questions pop up on exams of like, what's this insane number to the 0 power? And it's always 1. Okay, any other questions? Okay, sounds good. I'm going to stop recording really quick.